entertains me. Oh, here, just for one more extra opportunity not to do extra work, I will announce, I just hit record. The homework for week 12 is worth negative points. If you do and submit it, you will decrease your grade. Do not do homework 12. If you are not paying attention to my lectures, feel free to do extra work for negative points. There you go. Oh, you all, by the way, have the choice of, I mean, you actually go to the effort to show up and listen, presumably, right? You're here. So you have the choice of whether to tell the people who skip class and then say, hey, what happened? Hey, did we do anything today? You have the choice of whether to tell them not to do that. It will also be listed on the form. This form is worth negative points. And if people aren't doing the lecture, I figure they're also not going to read. Yeah. What? Gina, question? What if you already did? No, Gina, Gina. That's not homework 12. You did homework 11. No. I'm not going to retroactively assign something negative points. No. One more time for clarity. Week 12 homework, which will be due this Sunday, not the homework which was originally due yesterday. Week 12 homework will be a PDF that you download and complete and scan or whatever, and that should not be done unless you're ignoring my lectures. Okay? And you guys get to choose whether you tell the other people who aren't here and who don't pay attention what to do. Okay, so let's do energy. And in particular, let's do energy of springs. Half kx squared was reckon, people. I'm going to do a simpler problem first, then we will do the homework problem. Well, simpler problem depends on how you think about it. I will remind you that in this entire chapter, there's only, this entire module, we only ever do one thing. Change in total energy equals external work. That's it. That's the only thing we're doing. To do a change in total energy, you need to be able to find final energy and initial energy. And to talk about total work, you need to know what work is by external forces. If you could do that, if you could calculate change in final minus initial energy and set that equal to external work, if you can think about the concepts, you will get the same answer. You will get the same, you will do the same thing to get the correct answer every darn time. I strongly encourage you, you will generate 10, 15 different equations over the course. It will look different over the course of all the examples you do. Please, for the love of God, don't memorize the individual examples that you get out of these. The individual things apply to individual problems. The one and only sentence that you should actually memorize is delta equals external work. Okay, now let's practice that. I'm going to give you bananas. Maybe I'm going to drive you bananas or have already driven you bananas, but I'm also going to give you bananas. I'm going to drop the bananas on a scale. Boing, right? Those spring scales in the supermarket, yeah? Well, we don't want to damage the scale, right? So you're going to reach out and you're going to catch the scale and lower it smoothly and slowly towards this equilibrium point. Very noble of you to do. Can you picture this? Again, bananas are released onto a scale, but instead of allowing it to oscillate, we haven't done oscillations. That's next semester. And we could do this same problem later, next semester, next year at this time, in a different way instantly. What you will do is I'm going to say you're going to reach out your hand and you're going to exert a force upward on the scale, what do you call that? The plate? The thing holding the bananas to keep it from going beyond its equilibrium point. Hey, what's an equilibrium, by the way? What does equilibrium mean? Equal what? Be precise. Equal to zero. What is zero? What is equal? Neutral, yeah, but what's neutral? So position is always relative to something. What's the relative position that is equal to what? Force is what I was fishing for. When I say equilibrium, I mean the forces are balanced. In equilibrium to a physicist means no net force. I didn't define that this year, did I? You'll see that in online resources from time to time. They will say for Newton's first law, an object in equilibrium has a constant velocity is another way to say Newton's first law. If net force is 0, you move with constant velocity. Okay, so the bananas are in equilibrium when you release the scale at the end. What does that tell you about the spring force versus the weight force? Which one is bigger if they're in equilibrium? Google form B. Is the spring force upward bigger or is the weight force downward bigger if you take your hand away and it just sits there? Or are they equal, or do they both not exist, or what? Again, the picture, the sketch of what we're doing here is I'm encouraging you to reason about how you have taken your hand away and there's a medium compressed spring and the bananas are sitting in it. Man, that's artistic bananas. Good job, Ross. And I'm claiming that at this position, what do you call that? It's not the plate of the scale. Tray of the scale, the plate? Okay. You're really bright. Daw. Okay, so again, I'm asking you to reason. If I claim that the plate just sits there when you take your hand away, you have brought it to its equilibrium position, its central position, where things are in balance, things meaning forces. If there is no net force, then which force is winning? Weight force down or spring force upward? I will point out that there are two forces and the total force is 0. And most people have realized that if two things add up to 0, they must be equal, although with opposite signs. The weight force downward and the spring force upward have equal magnitudes. One is a negative force, one is a positive force. So, what's the weight equation? mg. What's the spring force equation? Not half kx squared, that's spring energy. It's the spring force equation. Well, if you don't know, you should look it up. That's an important thing to know. It's one of the things you can't just deduce. So I'm telling you, here's a hint for how to do this. You're going to release the plate of bananas at the point where weight equals spring force, and you should then be able to find out stuff from that. I'm going to give you the plate of bananas, the spring, the original position of the spring had the bananas up here. And what did I give? I gave too much before. I'm going to give K is 300 newtons per meter. I'm going to give you the spring constant there, and I'm going to give you that the bananas have a mass of, let's have a whole 2 kilos of bananas, or bananas, as the case may be. Okay, so once the spring is compressed, it goes down. And you are helping stop it. Here's you. Here's you. And you have helped bring it to rest at the equilibrium position. If you weren't there, if it weren't for you, it would have overshot the equilibrium position and vibrated, right? As you know, as everyone should have ever seen with a spring that's bouncing. Okay, Google question C. Apply what you have learned with work and energy. You have enough information to discover how much work must you do to lower the burners to tho to equilibrium position at a slow and steady speed. Um, just a word about the slow, steady speed. I'm going to let you do this. I'm not going to talk in one more second. If you let it go fast or if you let it go slow, you can get different answers here. I don't want you to think about kinetic energy. Yes, it's moving, but I'm going to say you're going to let this plate down gently, just like your last X. Let them down gently. And slowly enough that half mv squared is ignorable. Ignore kinetic energy. Yeah, it's technically got to be there, but screw it. Ignore it for this problem. Okay, I'm going to give you 5 minutes by the clock. Then I'm going to give you hints. And we're going to do the problem. Ready, set, go. Again, I'm asking for how much work must you do? Daisy, don't worry about it. It was, what does equilibrium say about force? Any questions visualizing? Richard, you can deduce that based on what's given. You absolutely need to, but you can find it. Okay, time for a round of hints. What form or forms do we start with? What do you start with? Is there a spring that's compressed at the beginning? No. No. I set the bananas on at the top where it's at not at equilibrium. I set the bananas at the top where the spring is fully extended, right? What I described? When I drop the bananas onto the scale doesn't start already compressed. Okay, so I release the bananas from rest. What about kinetic energy? Do I care about that? No, because the instructor specifically said to ignore it. Is there potential energy, gravitational potential energy? Yes, we are changing heights. I would choose to define the equilibrium, the final position as y equals 0. And then I would say that I start with mgh, gravitational potential energy. There's your E initial, mgh. What form or forms of energy do we have now? Is there a compressed spring? Yes, the spring has been pushed down by the weight of the bananas. The spring has compressed. What form of energy do you get? Half kx squared energy. What's x? What does x refer to? X and half kx squared refers to the meters, the distance the spring has been compressed or extended. If I say that this has moved down from height h, should I plug in for x? H. If I say that I started at mgh with h as my initial height and I moved down to h equals 0 to 0 height, then by how many meters has the spring compressed? H. If the bananas move by h meters, then the spring compresses h meters. Use the same variable for half kx squared as you use for mgh. Okay, so you've got the initial energy, you've got the final energy. If you know a final and an initial, you can always find the change in energy by saying energy final minus energy initial. What's the punchline to the one and only physics equation in this module? Total change in energy, change in total energy is equal to total external work. What is the one and only force that we haven't accounted for when we're talking about potential forms of potential energy? The hand. I mean, the question asks, how much work are you doing on this? That should be a hint that you are adding a work to the hand, adding a work to the bananas. So I just told you how to find the change, to write down an expression for the change in energy. You should set that equal to the work done by the hand. So how am I going to solve for work done by the hand? Do you know the force exerted by the hand, the distance exerted by the hand? How do you do a work if you don't know force and distance? Well, if I just told you delta E equals work, you don't need another equation to plug in for work. You can just do delta E equals work. Find delta E. That's all you got to do in this. You'll notice that H wasn't given. How did I start out this problem? What was I talking about at the beginning about what equilibrium means? What is happening when the spring is released at this point? Is it moving? Is it accelerating? Is there a net force? So what can you conclude about the kx spring force and the mg weight force? They're equal. That's right. That's how you find h. Ready, set, go. You have another 3 minutes. I have told you exactly how to solve every part of this problem. Just plug you into the equation. No, this is still C, Gina. I want to see if people can work on their answers. Damn it. Ow, 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 ow. Ooh, that doesn't feel good. Oh, oh. All right, so I gave the strategy before. Now let's see how to plug in numbers to do it. I'm going to work backwards up from the bottom. I said, the last thing I said was I can impose that the net force on the bananas at the equilibrium point, the bottom, is by definition 0. So the upward force of the spring minus the downward force of the weight is 0. Why KH instead of KX? Because I know how far the bananas have been compressed. That's what I'm looking for in this part. That distance is the height the bananas have moved from. If the bananas go down by H, then the spring compression X is H. Okay, well, I could plug in numbers. I gave you K, right? Did I say 300? 300. 300H minus, what's M? 2 times G is, oh my God, round 10. I have seen and received a lot of questions about algebra, so let me give you my fast track again for how to solve one variable equations in algebra. Screw PEMDAS. Take PEMDAS and shove it backwards. If this were PEMDASing, if we were evaluating, I would multiply 300 by H, then I'd subtract off, yeah? Screw PEMDAS. Do it exactly backwards from what PEMDAS says. If the subtraction is the last thing you would do, undo that first to solve algebraically. This is what you do every time you've got a one variable expression in algebra, unless it's a quadratic equation. So I'm going to say 300H. I'm going to get rid of the minus 20 by adding 20 to both sides. I add 20, I get rid of minus 20. Then I've got 300 attached to H, so I subtract 300 and I'm left with H, right? Right? I just subtract off the 300. No, I divided it. You have to ask yourself for each step, how is this attached? How do I want to remove it? Do the inverse operation. When I write 300h, what I'm saying is 300 times h. Do the opposite of multiplication, which is division. H equals 2/30. What's 2/30 roughly? 0.67? No, 0.067. I must have released it from 6.767 meters above the equilibrium point. Great, but this is force, and I want you to think about energy. Oh, sorry, that was too loud. I want you to think about energy, so let's go back and do it with energy land. Let's go back and apply this to energies. Again, the same question that I have asked in every single lecture up to this point in this module, and will ask in every single other time we do energy, is what form or forms do we start with and end with? As we discussed a minute ago, you start with positional energy. You end with spring compression energy. Why are the same variable? Because the same distance is the same distance. I can plug in numbers, by the way, M2, G, 10, H, 0.067. The 1.3. I'm going to keep a guard digit. It's actually 1.33. Okay. Equals half kh squared. I'm sorry. Energy final, not energy initial, equals half kh squared. What's that? 0.5 times what's k? I gave you 300 times what I gave you for. Ooh, my favorite number. Wait, that can't be. I thought energy initial always equals energy final. Is energy initial always equal to energy final? I mean, that was true in a whole bunch of examples we did before. Isn't the law of conservation of energy that energy never changes? No, the law of conservation of energy is that if energy changes, it changes by exactly the amount of work done externally. I didn't write it yet in this. I said it out loud. So I can write down my change in energy equation. Do I do final minus initial or initial minus final? So how much does my energy change? I can remind you, E final is 0.667. Energy initial was 1.33. Google, question D. How much work did my hand do? What? Which, if you did it right, should be the same answer as before. Please check your numbers. This should not be a difficult computation, but I've got half of the class missing something here. Please check your numbers. Oh, my dudes and dudettes and all of the states of dudism. Okay, my friends, what does delta E even mean? How can we calculate delta anything? If your bank account was $100 and now it's $50, how much did you earn, my friends? How much did your bank account change by? What is the increase in your bank account? You had 100, now you got 50. Did you go up by 50? If you agree that you went up by 50, that the change in your bank account is positive $50, then let's do some financial trading after class. I would love to help you invest your money if you believe that starting at 100 and ending at 50 is a change of positive 50. Final minus initial, 0.667 minus 1.333, negative 0.66, whatever. Okay, I'd like you to reflect on this a little bit. Which direction is your hand pushing on the bananas? Which direction is are the bananas going? What is the sign given those two directions? Google Form E, what is the sign of work given that the hand is pushing upwards and the bananas are displacing downwards? What must the sign be for any time that that combination of force and direction displacement are? Again, my question is, if you have a force which is going upward and an object which is displacing downward, what is the sign of that FD cos theta? Always. Signs cannot be left. By sign, I mean positive or negative, or zero. Positive and negative is also not a possible sign for a single value. Work is either positive or negative or zero. It cannot be both positive and negative. Perhaps writing the word cosine was a bad idea from the beginning. Do you guys know what the curly bracket means piecewise? I'm going to write what you multiply by as a text condition instead of as a cosine theta. Hurts? If it hurt that very badly. Okay, here is the definition of work again. Except instead of saying times cosine theta, which will actually be important if you're studying for MCAT, but let's get it right here for now. I'm only giving you three possibilities. The force is pushing in the same direction, the opposite direction, or at right angles. Which direction is the hand pushing on the bananas? Which direction are the bananas going? Or is that helping or hindering that displacement? The work when you are pushing in the opposite direction of motion is a negative work. So negative sign for this work that we calculated before by talking about change in total energy should make total sense. That's fine that it's negative work. So fine. So fine it blows even Ricky's mind. You guys don't know 50s music. Never mind. Hey, Ricky. Hey, Ricky. You're so fine. Sorry. I forgot. The university actually prohibited me from singing in class. Never mind. Okay. So, sorry. Mickey. Oh, that's why you didn't get my hilarious joke. Ever since Doctor Who season 32, I got Mickey and Ricky confused every damn time. Okay. Don't blame me. Blame Christopher Eccleston. So what is the point? The point is, as always, change in energy equals work done. If you can identify the forms of energy that you start with, end with, and can talk about what work is and means, this is a very straightforward thing. You must also remember that change means final minus initial, not initial minus final, not just a magnitude. I am 2 years younger than my wife. Yes, that is true. You can say Tucker is 2 years younger than his wife. But if you say what is delta age relative to Serenity, if Serenity is the reference point, it's not 2 years, it's negative 2 years. 2 years younger is negative 2 years older. How many years older am I than my kid? The 37? No, 39. I am 39 years older than my kid. How much older is my kid than me? He is negative 39 years older than I am. No, I screwed that up. 33. Whatever, screw it. Okay, so let's do a similar related problem, but not the same. Incidentally, if you use the same intermediate equation of KH minus mg and setting energy, this energy initial minus this energy final, sorry, the other way around, you will screw this up. You have to think about the forms of energy going into this and write the equation intelligently. Apply what makes sense to apply, and you will get the correct answer. Okay, so here I'm going to drop bananas. I'm going to drop bananas and they will pass through the equilibrium point because you are not there to save them. You died after your final. Womp womp. No, don't actually die after your final. You've got to be there to save the bananas, damn it. You're going to let the bananas fall. Oh, how could you, you monster. You let the bananas down and they go down, down, down till they turn around. Till there's such a big force on them that they spin back and then they go upward. In other words, I'm asking you to describe the oscillation. Well, we haven't talked about oscillatory behavior yet, but let me point out that if you don't do any work with your hand, the bananas will go down so far that all the initial height energy will turn into position energy. There you go. Same setup. Find the final position of the bananas. Using the same information. I'll state it from the beginning again. Mass of the bananas. I said 2, right? 2 kilos? Spring constant, 300. Wait, what's the very useful thing that we derived in the beginning? Height to the equilibrium point.
In class, no.
What is that, 6.7 centimeters? No. No. Height at the equilibrium point was 6.7 centimeters, not, that was the amount of energy. I think I'll put this on the test. If you guys concentrate on this and learn from this. Merry Christmas. Here's an exam problem. Merry Christmas. Doing your final exam for you. I don't think scales are this big, actually. Too big an oscillation. Whatever. And I'm going to give you time by the clock. 5 minutes. The answer is not in joules, my friends. How far is a distance question? I mean, that's the question. You should also think about just how big a meter is and if it makes sense for you to be going more than a meter. Like 20 meters is really quite far. Okay, so getting there. We got a lot of correct answers, but I'd like everybody to learn, not just half the class. So I'm going to build you up to it, and I'd like to try to find out where y'all are dying. Well, half of you are dying. So I wish you to tell me the following. Do not tell me a number. Do not tell me a formula. Do not tell me a word. For questions G and H, the correct answer can only be the letter or letters that we use to identify a kind of energy. That is to say, K, UG, and or UE are the only applicable answers, or some combination thereof. Now, as we discussed, and as I think you felt disgusted with before, gravitational potential energy, to answer a gravitational potential energy question unambiguously, you have to set a reference point. Previously, I said at the equilibrium position is the reference point, but now I'm letting you go down below the equilibrium position. So where should we set? You guys tell me, where do you want to set H equals 0? Where do you want to set the reference point for gravitational potential energy where we say there's no gravitational potential? At the middle point? At the top point? At the bottommost point? Where? Bottommost. Sure, it doesn't actually make a physics difference. We're going to define this height as y equals 0, okay? Relative to that, once you have decided on that reference point, these answers have a strictly correct form. So again, for G and H, tell me the form or forms of energy using K, UE, and UG to do. For question I, there is no form or forms of work. I just want you to tell me what force or forces are the external things that we haven't accounted for that do external work. Okay, what forces do we need to account for their work, if any? Do not, for the love of God, you know what? No, I'm just taking away points. People have ignored my instructions and they just lose points. You may ask your neighbor or may raise a hand and ask me if you think you may have completely ignored instructions and just typed in random shit. Yes, absolutely, Richard. Thank you for asking for clarification. For G and H, I am asking for the forms of energy. I do not want the equation. I do not want the word. I want the abbreviation K for kinetic, UE for elastic potential, UG for gravitational potential. Tell me what form or forms of energy. You can include multiples of those or nothing if there is no energy at that point. No, there are no forms of work, but there are which forces do work that we haven't accounted for. For I, you could tell me the kind of force that we haven't already accounted for in G and H. So what works does it make sense to talk about? What other forces acted on this that we're going to analyze? Okay, time's up. At the initial time, the high time, it is high time for you to analyze the high time. At the high time, we are above our 0 point. UG is very important. At the initial time, as described in the problem, we are not moving. There is no initial kinetic energy. K is incorrect. The spring has not yet been compressed. There is no elastic potential energy at the top. Initial total energy is strictly gravitational. At the most bottom point, you all decided that that's where y equals 0. What's mgy if y is 0? I hope you said 0. There is no gravitational potential wherever you choose to define the reference point as. The datum, the relative point to be. So there is no gravitational potential energy. Is it moving at the lowest point of its motion? Is it moving up when it's at its bottom? Is it moving down when it's at its bottom? No, it is temporarily at rest. If you were going down and are about to go up, your temporary instantaneous velocity is 0. So there is no kinetic energy at that time. Correct answer for bottom energy, the final energy, is strictly spring energy. The spring is compressed, very compressed. So again, the correct answers for G are gravitational potential, UG, and not kinetic, UE for the final. Now, riddle me this, Batman, as I am fond of saying. What other forces acted on this during this time? Did we have a solid surface pressing on it? Did the table touch the box? Did your hand touch the box? Did a cow come along and touch the box? So where the hell is the normal force? Normal force is solids touching things. We have accounted for the spring. We have accounted for weight. There is no normal here. Huh? If you do no work to save the bananas, I said you are far away. You do not participate in this. You are not touching now. I've changed the problem. This is the second part. There's no more you. The table pushes on the spring. The table exerts a normal force on the spring. I'm not analyzing the spring, I'm analyzing the box. Spring doesn't have a potential energy, a velocity, and so on. I don't know the mass of the spring. I can't analyze that. If I were talking about the spring, then sure. There would be a normal force of the table on it and a normal force of the box on it, I suppose. Question in the back, yeah. When? Gravity, the force of gravity absolutely does act on the bananas, but the whole idea of gravitational potential energy is how much energy can the force of gravity deliver to us at that point relative to some origin. If you are further and further up, you have more and more ability for gravity to push you further down. It's not that gravity's gone away. Gravitational potential energy is 0 does not mean that there is no gravity. If you take away the spring and dig a hole in the ground underneath it, you can pick up more and more speed. Gravitational potential energy can go negative, increasing your kinetic energy. It can fall into the hole. What matters for potential energies is not their number, but how they change. Meditate upon this, grasshopper, and come to enlightenment about the meaning of potential. Okay, I wish to move on. So you should know at this point what we just discussed. You start out with gravitational potential energy, you end with elastic potential energy, talk about the very top and very bottom of the motion. There is no normal force pushing on the box. Gravity, kinetic energy, spring energy will grab, Gravity and springs have already been accounted for. If we talk about the work done by these forces, we'll be double counting. Don't talk about an energy and the work done by that same force. The correct answer is there is no external work now. You've taken away U. The only forces acting on it are already accounted for. So what could I say? The same equation as always, Pinky. That's the change in total energy. I should, to be parallel. Plug in, solve. Ready, set, go. Or as my baby says, ready, set, go. This is Google question J. You got another shot at F. How did I word it before? What did I say before? I love that question, by the way. The lady in the back. Very, very important. Keegan, nah. It's fine, you can leave it out. If you got it right the first time, you don't have to do it again. Oh, make it easy for me to see when it's done. Yeah, if you're sure you got it right, if you know you got it right, do put it in J again anyway. That'll let me see when people are done and when they're still working. Again, I am looking for a distance. Don't tell me joules, please. The answer's up on the board. If you struggle with the algebra, please ask a question. Or if you struggle with any part of it, ask a question. All I'm doing is plugging in what I wrote above, plugging in the formulas that apply, and solving for the variable I wish for. Pregúntame, mis amigos. Frag mich. Did it. Then you are dismissed. Thank you.